Ah, my name is Zubair and I am doing my master's in electrical engineering and informatics with specialization in embedded systems. And this is my thesis one under Professor Domokoskis. And I'm doing my thesis on wall following robot for the thesis one. This is a robot node implementation. I have written a node in C++ in which a robot follows the wall of a certain environment. And I will tell you what softwares are, I will give you a brief idea what softwares I use, and I will tell you what environment I use, and later on I will show you how the robot behaves at the end. So the first thing that I use is ROS, that is Robot Operating System. So if you want to control a robot, you have to give your commands, you have to make robot do certain things. So this is the platform. Why? What is ROS? It's an open source software development kit for robotic applications, and it offers a standard software platform for developers across industries that carry them for research and prototyping all the way to the development and production. So it's a one-stop solution from the development to production. You use ROS all the time, and it's a better way. It's actually controlling the operating system of robots. It's an operating system controlling the operating system of robots. So like a firmware. So why ROS? Why I choose ROS? There are many other softwares because it's a global community. We use it for more than 10 years, and the ROS projects has produced vast ecosystems for software of robotics by nurturing global community. Means if you have some problems, you will not get stuck. Many people are using ROS. You can go to the internet, find your problems, and that's why it's very easier to use this, and you will get help from global community. And it's a proven in use. And it's relied upon for the robotics industry. It's a norm for teaching robotics. It's a basis for most robotic researchers, and from the students to the multi-institutional collaborations, they are using ROS. Also, it's 100% open source, so you can use ROS. And now we have the ROS operating system. And how do you create the environment? You will not take the real robot and put it somewhere. It's feasible to use a simulator. So I have used a gazebo. So gazebo is a 3D dynamic simulator with the ability to accurately and efficiently simulate populations of robots in complex indoor and outdoor environments. So what is actually gazebo? It is having everything: gravity, physical. You can create any kind of environment. You can create this building. You can create this classroom with every physical property existing in the nature. So also the gazebo is used for testing robotic algorithms, designing robots. You can design the robot inside the gazebo. Different types of robots, like mine is Go 3. You can create your own robot in gazebo. And it's used for designing tools, performing regression testing. Regression testing means when you are, when you are doing something different, you test the robot whether it's behaving normally or not. And also the more features of the gazebo are it's a multiple physics engine, a rich library, a variety of sensors available there, convenient for programmatic and graphical interfaces. So it's a great platform as a simulator to check how your robot is behaving. Now, after you have the knowledge of both the software part and you have the simulator, you just integrate the both. So it's a long setup. How I did it in this semester. First, I learned ROS, set up my ROS workspace, and I created projects for the simulated robot, created a gazebo world. Mine in the case is a below garage, which I will show at the end. And I created my own robot model, which was already created by the supervisor Go 3, so I used that one. And I connected my robot model to ROS. Then I used teleoperation mode to change the velocities of the robot, and added a camera to the robot. Here in my case, I have used a laser, and I used RBase to visualize how the robot is behaving, how the robot itself is seeing the external environment. So this is RBase. Now RBase is a useful platform. It's in Linux that I'm using. So it gives you, this is a wall here in this section, and it gives the robot idea about the laser sensors, how far you are from the given wall. Like here, lasers are going, there's no obstacle, but where there are more density of the lasers, you check, okay, there's an obstacle there, you have to stop. So I have, in this semester, I have to subscribe a node, publish and subscribe a node, so I have written a robot. I have written the node using these following steps. I set up the robot which follows walls of the below garage wall based on the inputs received from 360 degree resolving laser measuring nearby distances from the wall. So the robot it, it has a setup of laser which is revolving continuously 360 degrees, scattering the lasers and taking information how much you are from the walls. So second, we have set up some minimum threshold distance up to which the robot can navigate around the walls without colliding. So the robot when goes forward, it will know what is the minimum distance that I have to go close to the wall. To implement this, we have divided the laser range into robot, into right laser range, left laser range, and front laser range. Each of the sector having a span of 60 degrees. So if my robot is going forward, this is the section that is covered, that is the lasers are scattering. That I have focused on is 180 degrees, and I have broken down those 180 degrees to 60, from 60 to 120, and from 120 to 180. So the robot is going forward. So we have covered 180 degree span. Based on the minimum distance and the set of rules we set it for the three sectors of the lasers, we have implemented the algorithm that makes a robot to navigate around the walls without collision. So this is how ROS works. You write the node, there's a ROS master who takes all the information what you have done. If some other node needs the design, so it asks the ROS master and they can interchange the topic. So in our case, we are using the scanner that is representing the laser to use the communication between two nodes. And this is my algorithm. So first I have used the scanning. The laser is scattering the rays using this function. And I'm calling this function, and I'm setting the minimum threshold for the right as 0.4 meters, for the left as 0.4, and for the front I'm making it 0.8 meters. And I have used this logic of 8 different gate combinations. If my right minimum distance is less than threshold, my front minimum distance is less than threshold, and left minimum is less than threshold, then do this. Stop and just revolve. And I have these 8 combinations, and I have used the different velocities by checking the robot's behavior in gazebo. So this is my below garage world, and this is our robot Robigo. Now this is how it looks like. And okay, so this is the robot is when the robot is moving, it's continuously publishing what's the new minimum. And it's moving, the minimums are changing, and it's publishing the results in a terminal, telling if it's less than minimum, then it should turn. So the next one is this: when the robot goes forward, it checks and it follows the wall, follows the below garage successfully. So my future goal is navigation of robot under dynamic conditions. Now, till now, everything is dynamic, nothing is coming in front of robot. If there is static, not even static objects, in this semester, I have limited myself to only the walls. Now, in my second semester, for thesis second, I am using the dynamic environment in which some things are moving in front of robot, and the robot has to go from one point to another point. So it should behave normally, it should not collide, it should wait for the object to go and then pass on, or increase the speed if the object is coming very slowly. So this is my future goal, and thanks.
Thank you.
I want to show you the simulation if you won't allow me, because I have the.
Okay.
So I'm connected. I'm connected to the automation lab virtual machine. This is the robot. This is in the Linux environment. This is our robot, and I'm just running it on.
Just start, and then we can discuss the questions meanwhile it's running.
Yeah, it's running. Yeah, I'll just. If you see, it's turning and it's following the walls in this below the right wall. So that's it. That's what I want to show. Thank you.
Thank you. Any questions?
Can you please go back a couple of slides after the stuff? Yeah, here. Can you please tell me how do you connect this roads? Is it by broker when you publish?
First of all, how ROS works is there are different nodes. For example, I have written a node to follow the wall. There must be something different, doing something else. So there is a thing called ROS master. He should know everything what's happening in the system. So whenever you do ROS, if this node requires this information or this code, they do not directly exchange their information.
Well,
that's published. You cannot publish.
Yeah, this is the topic, the topic.
Yeah, this is the topic.
What technology is that like?
Topic is like which topic I have used. For example, I have used the scan like callback function in my algorithm. So it can be anything else for scan. If it's a laser, it can use scan.
Okay.
If it's something different, it can use that topic. So first I have to inform the ROS master, and it's also in communication with the ROS master, and the ROS master informs it, okay, I have it, then they start exchanging, they start publishing, okay, I have the scanner info, and this is subscribing to that info.
So it's implemented in C++.
Yeah, I'm not in C++.
That's what I wanted to know. Thank you.
Any more questions?
What was the most challenging part?
I'm new to robotics. It was a challenge. I've never used robotics in my life. I was a power system student in my bachelor's. I've always used power converters and all this. It was a new challenge, and I'm very thankful to Mr. Domokoskis. I didn't have the machine having Linux, and it was not so powerful. He set me up a machine in the lab having Linux, and I used to go there, learn ROS commands. Still, I'm learning. I'm still. It has a lot of contribution of Mr. Domokoskis. But I'm very happy that I have chosen this topic, and I will learn more and implement what I have.
This looks quite interesting.
And it was interesting.
Yeah. And so is it your project lab or
It's my thesis one.
this one? So you have only one semester.
I have one more semester, and I'm using the dynamic environment. If I'm successful, I may use machine learning in this part.
Yeah.
And I have a hardware as well. This GoPigo lies in the BME automation lab, and I will test it in the on the hardware as well.
Yeah, that would be the
I can test this thing. We can test it now, like in automation department, because the GoPigo 3 robot is available there. You just have to.
I see. And you also mentioned this path, or follow the path, or something like this.
Yeah,
I mean, I would like to go there, and you should try to do it somewhere.
Yeah.
Somehow.
If the robot has to go from this corner to this corner, and there are multiple objects moving around.
Yeah.
So in the next semester, I'm using a dynamic environment, not a static environment in which you will
Yeah,
not.
but if you have static environment and just going around, that is different as if you would have a certain destination point.
Yeah, you
But
can
was-
set in the gazebo, you can set the destination point.
Oh, so it's
and
already there.
Yeah, your robot can follow that destination point. It's not all, like you have the walls, it has to go there, and it will implement which is the closest wall, like in terms of
Yeah.
perimeter, and then your robot can go there.
So it's a little bit smart and try to use
Yeah, we're trying to be
Not
more
really
smart. Not,
the
yeah.
best, yeah. Okay. Thank you.
Thank you very much.
Our next one is why?
Yeah, I have registered twice because
Yeah.
it was a problem.
Okay. Then